Hello, everyone, and today I have an interview that I know a lot of you have been waiting for. I'm going to be talking with Andy Wright from eFabless about what went wrong with MPW 1, 2, 3, 4, and 5, what the fix was, and what steps have been taken to prevent these kinds of problems from happening in the future. We'll also be covering silicon validation, physical verification, timing, and the sign-off process. Andy Wright graduated as an EE in the mid-90s in Ireland and came to the US to work at Cypress Semiconductor. He's worked on every kind of product and IP block except radios. Along the road, Andy was the chip lead for PSOC3, which was the first S8 PDK product. Later, he was privileged to lead all design development at Cypress, and that was working with existing, newly acquired or merged teams to address quality issues, to standardize and to improve how they did design and product development. Since leaving Cypress, he's been developing microwatt IoT systems and MEMS integrated edge ML sensor ICs. He's now full-time at eFabless. So welcome everyone to an interview today with Andy Wright. Welcome, Andy.
Hi, Matt. Thank you for having me
on. So you joined the eFabless team how long ago?
5 months. 5 months.
Okay. Yeah.
And 4 as an employee.
Okay, great. So you're full-time there now?
I am, yes.
Right. And tell us a bit about your background.
27 years in semiconductor space or in the IoT embedded space. And I would say 40 years of electronics if you go back to, plugging Lego motors into the AC mains.
Nice.
So a lifetime of trying to do things with electronics.
And lots of magic smoke as well.
Lots of blue smoke.
Yeah. So talking of the blue smoke, that's really one of the main reasons we're here today to discuss kind of what went wrong with MPW 1, 2, 3, and 4 and what's been done to make sure that doesn't happen again.
Yep.
So maybe let's just start off with, can you tell us, because I had a go at attempting to explain this on my own channel, but I think I didn't really capture the whole picture. Well, we know more now. So could you explain what went wrong exactly with MPW 1? Why was it so hard to bring up? Where did the hold violations come from?
Got it. So I think there's a large set of small problems, and each of those problems contributed some amount to our ability to understand what was going on. The fundamental issue is that all of the simulations that we were doing internally were not reporting the hold violations that really existed. And if you break that down to a few different sources of problems, there were missing constraints in the simulation decks. There was a failure to back annotate. And originally in the development of the actual netlist, which would have worked even if the simulations hadn't had the layout been generated correctly, there was a failure to constrain the design in a way and buffer the design in a way that would result in good hold and setup performance. So we had 3 problems stacked on top of each other. The fundamental issue, the lack of the ability to see the issue in the netlist, and the lack of the constraint in the netlist analysis to be able to visualize in a simulation report that the problem existed. And all 3 of those problems stacked means that it's the kind of problem that a novice analysis is not going to find very quickly.
Right. And I understood, and I think probably most people understood the majority of what you just said there, but one thing that I'm not clear on still is, what does back annotation mean?
Got it. So in the process of extracting a netlist from a layout and then converting it into data that represents, let me call them the components, active and passive components, and the timing delay associated with the active and passive components, there is a step called back annotation. And annotation adds delays associated with parasitics, resistors, and capacitors to active component netlists. And in our extraction and back annotation flow, the extraction was working, but the step of back annotating the timing delays associated with the passive components was not correctly allocating the timing delays in any netlist that had hierarchy.
Okay. So one of the key problems that happened with MPW1 was we've had this problem with being able to set up the GPIOs, and they're done as a long scan chain, separate little blocks that are then connected with these wires. So even though the timing analysis was done on the blocks themselves, because the delays in the wires weren't back annotated into the top level timing model, the hold violations weren't spotted.
Correct. So the IO cell itself works, and the actual 13 registers associated with an IO cell, at least in the first generation of that netlist that I saw 5 months ago, functions correctly at its boundary. And the problem is when you instantiate that thing at a higher level and create setup and hold times at the boundary of the cell, and you don't represent the delays getting to that cell boundary correctly in the netlist, you can't see that there's an issue.
Right. One of the questions I always ask to people with a lot of experience in ASIC engineering is what was one of the biggest mess ups you saw, and like what went wrong? And I remember when I asked Harold Prettel, professor at JKU, he told me a story about all the main problems that people hit at the boundaries of things. Would you agree with that?
I would say that that's true to a very, very large extent. In fact, if you look at high-level systems problems, the problems that actually get out into the world, they're usually at organizational boundaries, right? So they're at places where a group is interfacing with another group. Inside of a design or a piece of semiconductor work, they're usually at the interfaces between tools. And then inside of an individual block, they're usually at the interfaces between small subcomponents, because people understand the individual components pretty well. So I think, the general statement, that's absolutely true. Right. In terms of the worst issue I've had, I actually can't say, not because I haven't got a list of them in my head, but because the top 2 or 3 issues are ones that I would get in trouble for talking about even now. I could give you a long list, but suffice to say that, if you drive any of the top European cars, at some point I've had some problem with any one of them. And if you drive any of the top Japanese cars, I could say the same thing. So there's a long list of blue smoke problems or problems associated with various components all across the world.
Yeah. I mean, I've got to say that it's very unfortunate, all the stuff that happened with the MPW 1 to 4 problems, but it is nice to be able to discuss them publicly, because normally that stuff is so secret. Like what you just said is so secret. People never admit that the tape out goes wrong. It's always kept like hush hush inside, because companies don't want their share values or them to kind of look like they don't know what they're doing. But you talk to anyone that works in a semiconductor company and they've all witnessed like tape outs that go wrong.
Yep. Yeah. I mean, I think that, in aggregate across the 130 nanometer domain now, the mask ratio in the industry is something like 1.1. So everybody is taping out, 10% of the masks again on average across the whole industry. And most companies have to do a second tape out to get something to production. So if people say there are no defects, they're being, just dishonest.
Yeah.
And they do have a process in the semiconductor space when you're developing commercial semiconductors that is very good at eliminating those defects before they get to the market. And that, I think, was the key difference, right? The opportunity to work through an iteration and clean the problems up before the customer base or the users are affected at all.
Yeah. So jumping back to, we spoke about MPW1. So like we got that back a while ago. Some of us managed to get things working anyway with very careful undervolting of the core voltage. I've got my clock on my desk that is working and is in my pride and joy.
Congratulations.
Yeah. But we've got MPW 2, 3, and 4, and they also have problems. So why? Before we go on to the why, what is the difference between the problems we had with MPW 1 and 2, 3, and 4?
Got it. So I can, at a very, very 10,000 foot kind of level, capture that. I think we identified the hold issue in the I/O ring on MPW1, and the fact that we were having an issue with the configuration chain registers associated with setting up the I/O channels. And what we didn't do was identify all of the net listing and back annotation issues that existed across the design. And so when we reanalyzed for MPW 2, 3, 4, we still had fundamental problems in the flow that hadn't been caught. And until they were caught, we were repeating some of the same issues that had existed in MPW1 without ever identifying that they were real. Now, to give 10 seconds of context here, this is all months or years prior to me arriving at the company, but the problem had been repeated several times before we got to do a real root cause analysis.
Right. Okay. So maybe now's a good time to talk about like, why did it go wrong? Because, I think, there's, I don't think people were really expecting everything to go like 100% right from the beginning,
Yep.
because so much is new. Like it was a new
Hmm.
and first ever open source PDK. It was a
Yep.
new RTL to GDS flow.
Well, yeah.
Um, there was loads of new stuff. Um,
Hmm.
so, but apart from the fact that like the pipes were being flushed and stuff, like why did it go wrong?
I think there was an element of developing the flow at the same time as our customers were learning how to use it. And there was an expectation that our customers were kind of going along with us for the experiment at the time in the company. And I think that what we've changed or what we've done to respond to the major problem is we've looked back and said, we have to behave and deliver a product that our customers can use, and they're experimenting, but we're delivering an environment they can be successful in. So approaching it from a higher quality bar going forward. And that's kind of the major change in direction.
And that was kind of the reason why you joined eFabulous, right?
Yeah, I got a call at the beginning of August, and Mike had gotten my name from somebody who'd worked in the same fab before, worked with the Skywater technology before, and he called me up and said, hey, I heard that you had done some work in this technology and had worked on some microcontrollers and this kind of problem before. And it sounded interesting, a technical problem that needed some help, and sounded like a good value proposition for the industry and for workforce development, for education as a whole. I thought it was a very good place to go. And so, I was looking at, do my skills map well to solving the problem? I think the answer is yes. I've solved lots of problems, but I was also the first guy to ever use this PDK. And so I was the person who was the pioneer chip lead on the what was previously called S8 platform at Cypress when the
That's
technology
Cypress,
was
right?
being
Yeah.
developed. Yeah, so I had both the subject matter kind of technical history with this specific technology and a very good understanding of how to take a flawed chip design and drive it towards a much better direction long term.
Okay. And do you think so? Yeah, maybe we can talk about like you're talking about driving it
Yeah,
to now be working
yeah.
correctly. Um, what's your confidence level for like post MPW, like MPW 5 and beyond?
So the ones that I've worked on, which is 6, 7, and beyond,
Hmm.
the confidence level is high, and I would say not at a confidence level that I would have had in an industrial environment with an unlimited tool suite and a much larger team, but an equivalent confidence level to what I've done elsewhere at startups. And so, industry appropriate for a startup company.
Right.
And so that's I think a good bar for where we are as a company and the appropriate bar for us to have shot for.
Yeah. Great. I'm glad. Happy to hear that.
it took a lot of work for the team,
Yeah.
right? All I had to do was help them find the issues. They had to figure out how to fix them all. So,
Yeah. Okay.
that's a
Yeah. So maybe we can spend a bit of time now talking about like what has been done to mitigate all these issues and to
yeah.
like make sure they don't happen again.
Got it. So at a start level, we started off with a methodology that I was taught by some lean practitioners, originally a guy at Honda. And it's called Genshi Genbutsu, but it means go to the workplace and see what's actually wrong. And so we started off looking at initially the MPW6 tape out database and trying to figure out whether it was ready to tape out or not. And our discovery process was to look at the analysis reports for the MPW6 tape out database from every run we've done and try to figure out were there any issues being reported. And it looked suspiciously good. So that was my initial red flag.
Not enough
Right?
stuff is failing.
No, there was very little surface visible failure. And usually when you go into a design review, the team can talk to you and they can tell you what they feel the issues are and they can identify the things you should be working on. I went in and it just sounded, it was like a boat or a car that was perfect. It's a used car and there's nothing wrong, right? And the probability is low. And so you start to dig the next level down under the surface. And after the first few reviews, and that was over a period of about 4 hours one morning, I concluded that we just needed to start at the beginning of the flow, literally data entry for RTL, and go from the very beginning of the flow to the tape out database and look at every input file, all of the execution code, and every output file for every step in the flow. And so that was what we did. We literally audited every step of the MPW6 tape-out database to try to identify the issues. And we went through every step in the flow, every input file, every execution code, and every piece of output, and every configuration file for all of those runs, and tried to find what was missing. And unfortunately, that process, as we now know, retroactively, uncovered quite a few things missing in the flow that needed to be addressed. And so we went off to try to work on fixing all of those things, and that was what led us to the MPW6-7 tape-out database.
Right. So if you had to choose the kind of the one most important thing that has been remedied,
Yep.
what would you say that was?
Subject matter or how we work? Because I think the most important thing is how we work.
One of each. I think that's
Okay.
a nice division as well.
Yeah, got it. At a subject matter level, I'd say the most important thing is to have the appropriate timing information in the netlist to be able to do analysis properly, and as a result, be able to produce correct results. At a how we work level, it's to always QA when we change a methodology or we develop a new methodology to benchmark that work versus the industry standard. So if we go develop a new PNR flow and it produces results, we check it versus an industry standard tool. If we go do a timing analysis and we do it with a new extraction flow and a new back annotation flow, we check it versus an industry benchmark tool and make sure that our tools are producing some results that make sense. Right? So that the open source flow gets to the point where it is good enough to produce comparable results quickly in the technologies as we bring them to market instead of after the fact.
Mm-hmm. Yeah. So I think maybe that's another thing that is worth mentioning is I think in-house eFabless didn't have, actually, I don't know. At the beginning, did eFabless have access to the industry standard tools to do these comparisons?
No. So there was a period of time in the life of the company where there was not, both for financial reasons and for just lack of access. A lack of good enough cooperation, the right tool suite for us to be able to get that benchmarking and comparison done.
Right. So yeah, that must be nice to be able to do those comparisons and kind of get that feeling like you're not missing anything.
Yeah, or at least we haven't missed something associated with that piece of the flow. We can rule out one more variable.
You're only missing what everyone else is missing.
Exactly.
Yeah.
Yeah.
Yeah, because I mean it is a complicated business, and I'm, as you know, I'm very new to this myself. I've only had 2 years as opposed to your 20 odd years. So I'm still learning stuff all the time. And I recently found out that when you do parasitic extraction on a GDS, it doesn't extract all the diodes. And I just thought, isn't that really too easy if you're doing a full custom analog for you to just short out the power rails with that and then never get any flags?
Yes. Yeah.
Apparently that's actually common in the commercial tool flows as well. They don't do it either.
If you don't draw a device properly and it doesn't fit into one of the characterized extractable devices, then that improperly drawn device is often not extracted at all as a device.
Just ignored. Yeah.
And so you need to be very careful that your DRC rules cover the scenarios of an improperly drawn device and prevent them from getting to the point where you're extracting the netlist.
Right.
Yep.
Okay, well, that is really good to have covered all of that. Thanks for going through that. Let's spend a bit more time talking about some of these other things we've got on the list.
Yep.
So is there one of those in particular that you would like to spend some time talking about?
I think the silicon validation is probably the one that's kind of helped the user base the most in the short term.
Okay.
And if you look at where we were, the first silicon, we had a Caravel board, but we had very limited provision of capability for people to bring things up in MPW1.
So let's just back out one step and say, what is silicon validation?
Got it. Okay. So let me describe three major steps that happen to a piece of silicon in a normal company after it comes back from being taped out and arriving as a packaged part to the engineering team. First is silicon validation, second is silicon test, and the third is silicon qualification. So silicon validation establishes that the chip does what it was expected to do. And that's not this specific instance of the chip, but the chip generically. It may take 10 chips for you to prove that that's true if there's a defect in each one of them. Silicon test is establishing, is there a test defect associated with literally defectivity or little particles in the fab that have landed during the processing of the wafer or misprocessing of the wafer. And then silicon qualification is establishing that the device will be reliable for its expected lifetime. It'll survive, some level of ESD zapping. It'll survive being heated and cooled the number of times it's supposed to survive, or being, exposed to some level of high voltage, and it'll survive moisture environment, etc. So in the silicon validation space, that validation can be done for some very simple structured parts like a RAM. It can be done on a tester very easily. But for a more complicated part, or a part that has a lot more capability, you usually need a board environment that you're going to test the thing in, and you need to figure out a way to drive vectors or data against the pins to do something, for a reasonably long time to check out that you've got the functionality that you need. Usually a tester, what's called a big iron tester, is not the right platform for that, because it's very, very expensive capital, and using it for a long time to check out that the chip does what it wants to do is a very expensive way of solving the problem. And so in the application space, in semiconductor bring-up world, there's usually an applications board that's used for silicon application validation. You're checking that the chip does what it was supposed to do. All the functions are there, but you're not testing the quality of this specific chip or testing the qualification for long-term reliability. And we had no nice environment for doing that validation bring up, and certainly not one that was kind of aimed at enabling a large user base at a reasonable price point.
A large user base of beginners.
Yes, of novices to the world at a reasonable price point. And so, at least in this, in most recent arrival of silicon on MPW2, we've worked to try to get a Nucleo environment out to everybody with the Caravel hat on it and the little, plug-in device. And that is to try to bridge that gap. Our end goal is something a little bit prettier, but this is definitely going in the right direction. And it appears that the combination of that Nucleo plus hat board capability plus the analog analog Discovery 2 box capability seems to be a price point and a capability that a large portion of our users are settling on as reasonable. Certainly the university and school user base, or university and two-year college user base, feel that's a very reasonable price point. And that's kind of a good arrival for the first effort going out to market.
Great. Silicon validation.
Yeah. Checking that it does what it's supposed to do.
Yes. Yeah. And then you need to get the hot air and the cold air machine and the vibration and the salt tank.
That's where you're going from. You're right at the boundary between validation and test there.
Yeah. Yep. Okay. So, Andy, what can you tell us about physical verification as it applies to the ASIC world?
Got it. So physical verification is the process of verifying that the layers that you're putting onto the mask are going to result in the behavior you're expecting from the silicon. And examples of things that you would try to isolate or eliminate with physical verification. A great example is the diode that you previously talked about with two layers stacked on top of each other. They didn't make an actual device, but they created a parasitic short to ground. And so that's the kind of thing you want to eliminate through physical verification. In our world, we have an amount of physical verification that's capable, enabled by the open source PDK and previously derived from what existed in the Sky 130 PDK. We also are developing, and you've probably seen, I think, some talk on the channel about developing and working on an LVS capability and a cross-voltage verification capability that Mitch Bailey is working on. Mm-hmm. That's kind of a long-term vector for MPW 8+, that we would like to add as something that certainly the analog and digital users try prior to tape out. And ideally, we'd like to get to the point where anybody who's not creating a new device, they're not creating a new inductor or creating some new component that didn't already exist in the PDK, for all the users not creating a new device, we'd really like to be able to see those extra verifications that Mitch is now working on passing before the user design comes to tape out, because they have been a very good indicator of quality issues, especially in the analog designs.
Yeah, because we've seen some designs where things like designs weren't powered.
We have seen unpowered designs. We've seen designs with very obvious, what's classically called a soft connect, but it's usually a connection between two different power regions where one of them is powered explicitly and the other one is being powered through diffusion or through the wafer substrate. And so they're poorly powered, and there's a high probability that they're not going to work correctly. And we've also seen devices with extremely long Li, so examples of devices where there's a very high impedance in the power supply, and the probability is that when the device switches, it's not going to perform the same way as the models are expecting because there's a large IR drop.
Right.
Okay.
Anything else you want to say on physical verification?
Specifically on physical verification, no.
Okay, great.
Yeah.
And then let's hit one more topic.
Yeah.
So I'd like to hear your thoughts on the process side of things, like the sign-off and documentation. I think that's
Yeah.
a really crucial part, and maybe also that was one of the things that contributed to the MPW 1 to 4 mess up.
Yeah, so our, having gone through the earlier Genshi Genbutsu process, looking at all of the things that were wrong, what you try to do is define when in the business process, when in the process of developing a chip from a technical perspective, should you have found each of those problems? What's the earliest point in the process that you could find it without adding excess work, right? And obviously you don't want to do too much verification. Verification costs money and you don't get paid for it. But you want to make sure you add enough verification to eliminate the defects or prevent them from happening. And ideally, you want to prevent them structurally at the get-go by having a method that just never creates the defects, right? So in an ideal world, you set yourself up with the right information at each point in time in the flow to be able to ensure that the next step is by definition clean, right? And the process that we create to do that has checks around the constraints at the start of the flow, around the configuration at the start of the flow, around the architecture, how we're buffering and how we're routing and how the chip is designed at the start of the flow, such that the flow then runs clean. And what we've been trying to do is parse when those different checks should happen and develop an internal business process. We're actually in the middle of that right now as a company. But we also are expecting to be able to deliver a simple process to the users to help them go through the flow and have a higher probability of user design success, right? So it's a big thing to take a novice electronics user and have them get through a flow, even something as simple as this, get through a flow and produce a chip that has a good probability of working, right? And our normal probability in the industry on 130 nanometer for one IP block is about 98 to 99%, and that's with industry qualified people. Okay, so about 98 to 99% of blocks have made it to silicon and worked on first pass good enough to be able to sample. Okay, that's pretty high probability, right? But if you take the same problem and you pass it to novices in the design space with no process and an open source PDK, that probability is obviously much lower. We would like to build an environment that they can work in where they have a much better chance of success. And so our hope is in the next couple of months to be able to deliver along with the chip ignite flow, a simple checklist set that the user can go through to help them be successful.
Yeah, I think that sounds like a great idea. Because if you don't know what you don't know, then how would you know what to make sure that you've done?
Yeah, that is the fundamental problem, right? If the list is too big for you to understand it casually and nobody's ever provided it to you, how can you be sure you're done?
Yeah. So some level of sign-off, I think, is a really good idea. That's a great, good thing that resource that eFabless can provide.
We did actually create the checklist for the tape out.
Nice.
That was the first one we created.
Okay, so we've still got a bit of time left. So why don't we have one final topic before we end?
Okay.
Let's talk about a bit more about timing. Because there's so much in there, and that was one of the key things also that bit MPW 1 and 1 to 4.
Yep, got it. So if I start at the beginning of the flow and talk about where timing happens as you go through the flow, there are many steps where timing interfaces to how you develop. At the beginning of the flow, you architect the chip that's possible in this PDK. Right, so you have to have some understanding of what, from a technology perspective, this technology is capable of delivering, and you have to, at the boundary of the chip, define chip constraints that are feasible. Right, in our case, that's a 20 to 40 megahertz type cycle time, it's roughly these kind of propagation delays between registers, this kind of memory is possible, etc. Right? So that architectural step has to happen. Then you have to parse the architecture into something that you're going to use to implement the chip. That's choosing how you're going to break the block boundaries, where you're going to route between things, how those routes are going to be buffered, or how the chip is going to be assembled in a way that it can be analyzed for timing sensibly. And ideally, you'd like to have, in the perfect ASIC world, there's just I/O cells and PNR. Right? That's the perfect ASIC world, because in that world, the only timing model that you have to put into the database other than the standard cells is the I/O cell timing model. And that's the simplest possible environment. Unfortunately, we had a hierarchical chip with far more IP than that. And in our flow, we had issues associated with how the hierarchical netlist was extracted, but we also had issues because our hierarchical flow wasn't buffering correctly between blocks. It couldn't see the timing delay because of the back annotation problem, and therefore wasn't buffering to solve setup and hold problems. So we had to solve the problem of allowing it to see things and then solve the problem of getting it buffered correctly. And that required some re-architecture of how we assembled the chip and re-architecture of the flow for how we were going to go do the work. And in terms of the next step, you've got an RTL database that meets its logic verification. Then you get to a gate level netlist, and that's the first time in the logic flow that you can run timing. So you've now got a verified RTL netlist that's at least cycle correct. You instantiate a gate flow that's been synthesized. You've got gate level netlist. You can do first timing checks on your gate level netlist. Then you go through a layout process where you create a layout, you extract the layout, you back annotate the layout netlist with the parasitics, and you take that and you run the gate level netlist with SDF, or you take that back annotated netlist and you run static timing analysis on it. So you could have the pre-layout netlist with gates and static timing analysis, or you could have the post-layout netlist with back annotated gates, SDF netlist, and timing analysis, STF, or you can do STA, static timing analysis. The difference between the static timing analysis flow and the gate level netlist flow in a logic verification simulations, the static timing analysis flow is trying every possible timing arc in every direction with a constraint set that you've provided to it. The gate level netlist simulation is trying the paths that you're explicitly stimulating in the simulation vectors. Right? So the gate level netlist, while it's a more accurate simulation methodology, it has much lower coverage in a given amount of time. Right? So it takes much more time and much more work to be able to develop enough vectors to cover everything in the gate level methodology. It's also a much more expensive tool per unit time to run, usually when you're paying for commercial EDA. And in the open source world, we can throw more tools at it. And because the tools are free, the only thing we're paying for is the cloud hardware. So we can approach the problem both from a gate level netlist verification perspective with SDF and from an STA perspective. Our miss was that we didn't have this simulation covered in an SDF sim in the original tapeout with the extracted netlist back annotated properly. The simulation existed, but the SDF didn't exist. And in the STA, which should also have found the problem, there are two constraints that were missing. So we didn't have the verification of the back annotated parasitics in the STA netlist either, because it's the same source of parasitics. We also were missing two constraints. The clock pin that was used to drive the I/O timing parasitic was not identified as a clock pin in the very first set of constraints that we used to be able to do the tape out. And the what's called a bit bank clock, the internal data-driven clock, which is literally just toggling a register to generate a data clock internally, was also not identified as an alternative clock source. And because neither of those clocks were identified, there was no hold time being measured to those registers for either clock source.
So that was like a problem with writing the constraints file.
Writing the constraints and understanding that we didn't just need constraints for the operation of the user mode, we needed constraints for all of the configuration and setup of the chip.
Wow.
Okay, so people understanding what needed to be present and understanding how to check not just that there was something, but that the something was complete enough. Right? And complete problems are hard. Right? If you don't have an experience base doing this kind of thing, that's a much harder problem to solve.
Yeah. Yeah, and a great point about like the difference between static and dynamic testing and how long it takes to do like a gate level simulation compared to a static timing analysis.
Yeah, our static timing analysis for the Caravel retape out was done on the order of an hour. our SDF back annotated gate level netlist simulations took about 2.5 days.
Yeah.
With the amount of hardware and compute license we can throw at it. So that's an indication of rough scope, right? You're talking about a 50x difference in terms of the compute overhead of getting those two things done.
Not the kind of thing you want to leave till the last minute.
No, and not something you'd like to discover. You don't want to discover simple problems like a missing constraint on the back annotated netlist at the end. You'd like to discover those simple problems on the very first gate level netlist and be able to understand where you complete enough or not.
Yeah. So that goes back to the point about process, like making sure that these checks are like signed off as you work your way through doing a design.
Yeah, so there's some very simple steps associated with how do you define the constraints in a design. And part of the process of going through the review with Genshi Genbutsu, going through actually looking at the flows was, did we constrain every pin, right? Did we constrain every register in the design, right? Because if you don't have a constraint on every pin and every register, something's fundamentally wrong. And you need to understand why it is that those constraints are not present. And that was what we were going for. And if we have pins that we're expecting to use for something, are the registers that they're expecting to be used with being constrained by those pins or interacting with those pins in our constraints file? If those constraint matches are not present, you know something's missing. And that's literally a review of, is every clock identified? Is every input identified? Is every output identified? And is the clock domain, the region that is affected by each clock, identified?
Great. Well, Andy, thanks so much for your time today with going through all of this in such great detail. It's really good to get a better understanding and to share that out publicly. Like we said, the open source tools have a great capability of making these things more available to more people. But obviously,
much more accessible. Yeah.
We also want the quality of results to be at a high level as well. And that's something
Our expectation is that we're getting there very quickly, right? So we expect that on the Sky 130 platform, we can deliver a comparable, and specifically on this open source platform, we can deliver a comparable result for a 130 nanometer device to what you would be able to get out of commercial tools. And that's what we're trying to get to very, very fast, right? And it's certainly past the point where we can deliver basic prototypes in this latest generation of tape out. We have to see it come back to be able to declare success, right? But the flow and the methodology that we're now applying is equivalent to the kinds of methodologies that would have been applied in a commercial environment. And that's different than where we were before.
Yeah.
And so what our goals going forward is, apply those steps at the get-go in each of the future technologies. So when we jumped into GF 180, all of this knowledge and methodology improvement, the flows, the checklist, the timing verification methodology, the constraints verification methodology, that was all applied for the very first GF 180 database development. So those guys will benefit from all of the learning that happened painfully on MPW 1 through 6 and see it all hopefully at the beginning.
Great. Okay. Well, thanks again for your time, Andy.
Thank you very much, Matt. Take care.
Bye.